All right. Hi, everyone. My name is Karel Hausmann. I will be chairing this session together with Roberto Calandra, who is joining us online, who will be handling the online questions. I hope you all enjoy the poster session. And we'll start with the first tutorial, which will be given by Byron Woods, who is here with us. Byron is an associate professor at the University of Washington. He's also a principal scientist at NVIDIA. Before this, he was an assistant professor at Georgia Tech. He does research across many different fields: machine learning, robotics, control theory, and others. And he always has really good insights how these fields interact with each other. And he will tell us a little bit about this today at the tutorial. So let's welcome Byron.
All right, thanks, Carol. Yeah, thank you for the kind introduction. Let's see how these slides work. Okay, so great. So before diving into what I've prepared for today, I just want to give you a brief overview of my goals for this tutorial. So after all, model predictive control and machine learning are really expansive fields. And there's no hope in providing even reasonable coverage of either one. So instead, today I'm going to provide a personal perspective, just the way that I think about these areas, for better or for worse. And my goals are to provide a quick introduction to the concepts behind MPC, so I'm going to do that first. And then I'll present several case studies which show really different machine learning perspectives on model predictive control. And my hope is that this opens the door to discussion, new ideas, and new ways of thinking and building better learning and control algorithms for robotic systems. Okay, so let's get started. So basically, to introduce model predictive control, let's consider an autonomous racing task where the goal is to design a policy to minimize lap time. So the image that you see up here on the slide in the upper right is basically an illustration of an overhead view of a race car on a track. Sometimes a little bit weird looking, so thought I'd try to clarify that. And let's say that we're trying to drive this car around the track and minimize lap time. And we can say that we can control the car by, for example, modulating steering, brakes, and throttle commands. So these are the actions that I can use to control the vehicle. So while formulating this problem, we may want to add a number of costs and constraints that we think are useful for minimizing lap time. So for example, maybe we want to maximize velocity since this seems correlated with traversing the track as quickly as possible. And we may also want to minimize acceleration so that we have smooth, energy-efficient motion. And it seems like staying near the center of the track is a good idea so that we're less likely to leave the track and crash. And we might imagine other choices for costs and constraints as well. All right, but here's the major question. Once we have all these costs and constraints, how might we derive a strategy for actually driving this car? Now, one thing we can do is use a model or a simulator to predict the effect of sequences of actions on the vehicle as it's racing around the track. So for example, we may want to predict that, well, we in general want to maximize velocity. Doing so around a tight turn might lead the vehicle to crash. So in other words, we're going to think about using simulation to basically optimize to find an open loop sequence of actions. We can think about this as kind of like a plan that minimizes costs and obeys constraints. And the resulting actions might produce a trajectory which looks something like this, right? So, okay, so just in summary, in order to do something like minimize lap time or do well in my task, I'm proposing to optimize in simulation and then find the plan consisting of the sequence of actions which achieves my task objectives. So this seems great, but what if our simulator is imperfect? So for example, let's say I execute the first action in my optimized sequence with the expectation that the car will move as indicated by the orange arrow up here on the track. However, when I actually execute the command which should achieve that motion, maybe the car actually follows the blue arrow instead. And this might be due to something like improperly modeled wheel slip. And this is bad now because my car is moved off of where I expected it to be, and it actually means that now the whole rest of my plan is wrong. It assumed that I moved according to the orange arrow when in fact I did not. And this happens all the time in robotics, right? Like, we expect the robot to move one way, and then it actually does something very different. So how do we deal with something like this? So to handle this, we first need to understand where we actually ended up. So we introduced this concept of feedback, maybe from a state estimator or something like this, which tells us where we actually are on the track after executing that first action. So once we know this, we need to replan from the actual car's location, and then generate a new trajectory, maybe something like this. We can then execute the first action on this new trajectory, and then continue this process, right? So now if we look at how we generated behavior over like this last couple clicks of my clicker here, it really boils down to a straightforward optimization-centric strategy. So first we plan forward from the current state in simulation. We execute the first action on the plan. We observe how the state has actually changed. And then we replan from the new location, and so on and so forth, right? We just repeat that process. So this is the core idea behind model predictive control. Another point that I just want to make is, if you're kind of thinking about this, you might think, well, it seems like this will be really computationally expensive because we're constantly replanning. Like literally at every time step, we're replanning. But if we also think about how this kind of replanning works and how we're expecting to be perturbed at every step, maybe we don't need to actually plan for the entire horizon of the problem. So instead, we can look ahead just far enough to make a sensible decision at our current state. And so this is why model predictive control is also called receding horizon control. So we generally only plan for a limited horizon into the future at each time step. So for example, at our state at time t, we might optimize to find the best sequence of actions for a horizon of length h. We then execute the first step of this plan, observe the next state at time t plus 1, and then optimize for the horizon again, execute the first action, and then we just repeat this process over and over again. Okay, so the horizon is always extending out h time steps in front of where we are, so h time steps into the future. And note that we're constantly using feedback, so we're re-estimating where we are in the world, we're re-estimating our state. And this feedback allows us to, at each time step, minimize this expected future cost in simulation while the robot is running. And this makes the approach really agile and resilient, right? So it's really useful if we have something like a robot which is operating in a dynamic and uncertain environment or experiencing difficult to predict perturbations. We just need a good state estimator to kind of figure out like where we are, and then we can just keep churning, just keep replanning. However, this is also, as you can imagine, computationally demanding because we have to solve this potentially difficult optimization problem at every single time step in simulation while the robot is running. Okay, so to describe MPC a bit more formally, I just want to sort of walk through what the optimization problem sometimes looks like. So at each time step, we want to optimize for a horizon H trajectory in action space from our current state. And this is usually formalized as trying to minimize the sum of future costs, subject to our current state, an approximate model of the system dynamics, and hard or soft constraints defined on our state. So for example, things like don't crash or don't intersect with an obstacle, or constraints on actions like obeying joint or acceleration limits. We'll then try to solve the optimization problem, and there's many different possible ways of doing this. So we could use, for example, quadratic programming, or stochastic optimization, or something else in order to get our plan. And then we do just what we've been saying before, right? So we execute the first action, we receive feedback from our state estimator, and then we return to step one and just repeat this process and solve the optimization problem all over again. Okay, so that's basically model predictive control in a nutshell in just a few minutes. That's what's kind of going on behind a lot of the MPC algorithms that you'll see in papers which are here at the conference, just kind of at a high level. Now, I want to talk a little bit about where model predictive control has traditionally been used and why I think that's changing some. So MPC is a particularly practical and fairly simple to implement procedure, and it's been used in a really wide range of control problems in industry, including a number of things that you see I've put up here on the slide. So chemical plants and refineries, food processing, automotive engineering, healthcare, power systems, aerospace engineering, HVAC systems for, you can think about this as like building control. So it's used all over the place. However, in sort of traditionally, MPC has often been used with fairly simple dynamics, maybe linearizable dynamics, with the goal of driving a system to a set point or a reference trajectory. So the way, the type of optimization problem that we're solving, the objective, is generally like pretty straightforward. But things have changed a little bit, like over time, right? So this isn't the 70s or 80s anymore. We now have really fast simulators and massive amounts of compute, and we can solve all sorts of complicated problems with nonlinear dynamics and complex cost functions, and we can do it really fast. And this is one reason, actually, why it may be extremely useful for controlling robotic systems. So in particular, like one of the places where we found model predictive control to be particularly effective is for controlling fast, dynamic robots in very uncertain and hard to model environments. So I just want to give a few examples of where we've used model predictive control in our lab. It's actually the basis for most of the robotic systems that we deploy. We're using like MPC somewhere in sort of the middle or lower level of our autonomy stacks. So some of you may have seen that we've used it as a basis for racing 1/5 scale cars on dirt tracks, and I'll talk about this a little bit more later. But note that the dynamics of this vehicle are really hard to model. You can see it sort of bouncing and sliding. But with fast MPC, we're constantly receiving feedback about the vehicle's attitude, allowing it to adjust as it experiences all of these perturbations. And from this, we can adopt a really aggressive racing strategy. So more recently, we've been using MPC to control 7 degree of freedom robot arms that are interacting with unpredictable humans. So here we're optimizing for trajectories in configuration space while estimating the changing state of the world in real time. As you've seen a little bit earlier today from Yu Sheng's presentation, MPC is also a powerful tool for locomotion. So here we're using a low-level MPC strategy for torque control of a quadruped. It's solving a constrained convex optimization problem at a really high frequency, allowing the robot to contend with uneven terrain like the loose rocks as it sort of scrambles along the edge of this path. And then finally, we've been using MPC for the control of larger ground vehicles as well, like this skid steer, ClearPath, Warthog, to robustly traverse wet and muddy terrain and things like compliant vegetation while autonomously avoiding obstacles and staying near a global plan to GPS waypoints. As you can tell, it's been raining a lot in Seattle recently, so everything is soaking wet, but that means there's lots of slip and cool stuff for the robot to deal with. So this has allowed us to use a single strategy that works really well in a wide variety of terrain, including things like dense forests and ice and snow. Okay. So I hope I've convinced you that MPC is an effective strategy for controlling robotic systems. It's super powerful on its own, and with proper tuning and proper modeling of the dynamics, you can robustly control robots in a really wide variety of conditions without really having to rely on learning for anything. So all we need is a reasonably good model and like a lot of compute resources that we can throw at it at every time step. So it's a good baseline. But I think there's a really big opportunity to control or to combine model predictive control with data, which is collected while a robot is operating, to develop even more effective strategies for autonomy. And so this way of thinking about it, it basically can provide a bridge between theoretically powerful machine learning strategies and the sort of real-world robotics tasks that we all care about. So today, I'm going to provide a sampling of 3 very different machine learning perspectives on model predictive control and think about how they can be basically combined with machine learning in these sort of interesting ways. So first, I want to consider what is probably the most obvious way to combine learning and MPC, which is that we can use learning to find the model that we use within the MPC algorithm. So I think about this as using machine learning inside of MPC because we're learning a component of the model predictive control algorithm. Next, I want to change our point of view and consider the model predictive control process itself. And this is super interesting because it's possible to view MPC as a machine learning algorithm, specifically as an online learning algorithm, which is rapidly modifying a policy as it's executing. And from this perspective, we can easily develop new MPC algorithms and sort of fine-tune them to have the properties that we desire for a particular task. And then finally, I'll present a way to overcome some of the limitations of MPC through the use of reinforcement learning, allowing our robot to continually improve its control strategy as it encounters more and more data. All right, so let's start by just taking a look at this first idea. And to do this, I'm going to discuss basically the idea of learning a dynamics model within this sort of case study where we have a challenging task of aggressive off-road driving. So here's basically the robot that we're going to be using. So it's a high-speed off-road ground vehicle built in collaboration with several labs in computing and aerospace engineering at Georgia Tech. And our goal is to autonomously race this vehicle faster than a human can pilot it on dirt tracks. And you already saw a bit of a video of this earlier. So just to give you a little bit more of an idea of what this robot looks like, it's basically a 1/5 scale truck, so it's about 1 meter long. It's about like this big. It weighs roughly 45 pounds. It has electric motors, which give it a top speed of almost 60 miles an hour. And then it's a very capable sensing platform. So we have cameras, IMU, GPS, wheel speed sensors, LiDAR on board some of these vehicles. It also has considerable onboard computational resources. So we're going to do all of our processing onboard the vehicle so that there's no latency at all from communication or anything like that, or less, let's say. In particular, it has a GPU on board, which we can leverage in order to make MPC really fast. So we can control the car by modulating steering and throttle. And the question now is, how do we design a policy that will allow us to pilot the car at high speeds over rough terrain? Okay, so first let's look at why this is hard. So here what you're going to see is basically a video of the car driving in slow-mo. So this is 1/4 speed. And you can see that it's bouncing and slipping, and the behavior is quite difficult to predict, which actually makes it a perfect candidate for MPC. The whole key to this is having basically a good state estimation algorithm. So our autonomy stack looks something like this. So we have perception, which is based on a differential GPS and an IMU, which gives it accurate outdoor position to within a few centimeters. We're localizing the robot with respect to a map, which is computed from a GPS survey of the environment. And this allows us to get that really fast, accurate feedback while the vehicle is racing. And then we use model predictive control in order to generate actions. So in the introduction to MPC that I gave a bit earlier, I basically said that we want to optimize to find a good control sequence. But how do we actually do this? There are many different possible ways of setting up and solving this optimization problem. And traditionally, MPC relies on convex optimization. But for more interesting tasks in robotics, we may want an approach which works with non-convex costs and nonlinear dynamics. And one of the methods that we've found to work really well for this is an algorithm called model predictive path integral control. So MPPI is a sampling-based approach to model predictive control. And the method basically works by first sampling trajectories over some horizon h in the robot's action space from a multivariate Gaussian distribution with some mean mu that we have at a particular time step and covariance. So we're just sampling sequences of actions from this probability distribution. Okay, now given the state and a fast simulator, represented here by the model f hat, we're going to apply the action sequence to generate sequence of states, right? So with a starting state and an open loop action sequence, we can just feed it through the simulator in order to generate a state sequence. And this then gives us a whole bunch of predictions of different possible state action trajectories that the vehicle could be taking out, h steps into the future. We then are going to evaluate the cost of each state action trajectory. And so for the vehicle, the costs are things like drive fast, stay near the center of the track, minimize acceleration, and so on. We then compute a weighted average of the trajectories according to their desirability, which gives us a smooth, low-cost trajectory. And this can also be viewed as an update to the mean of the Gaussian that we originally used to sample our action sequences. So for those of you who are familiar with CMA-ES, this is actually a really similar approach, just used in this model predictive control context. Okay, we then execute the first action of the new trajectory, observe a new state, and then repeat the process after updating state using the previous trajectory as a warm start. So you can see what this looks like for our racing task here. I know it's a little dark and hard to see. But you can see that at each time step t, basically, we're rolling out almost 2,000 trajectories, like ahead of the robot, in simulation, indicating where the vehicle may be as it's racing around the track. And these are then evaluated to determine cost, and we have this kind of weighted average, which gives us a smooth, low-cost trajectory. And then that serves as a mean for the sampling at the next time step. So we're going to get something which looks kind of like this, with this spray of predictions out in front of the robot. Okay. All right. So MPPI can actually be really, really fast if you implement it on a GPU. So sampling trajectories is, if you think about it, a naturally parallel task. And so this is something where we can actually sample huge numbers of trajectories in real time on a GPU. And so for our robots, we can sample like literally thousands of trajectories at 50 hertz or higher when we're trying to complete these tasks. Okay, so this is all great. We can implement a really fast version of MPC, which is particularly effective for these dynamic tasks. But the question is, how do we actually model the vehicle given how complicated the dynamics seem to be, right? We saw that video earlier. So one thing we could do is just use a really simple kinematics model, something like a bicycle model, and hope that MPC just takes care of the rest. And this actually works really well for less aggressive driving. But for high-speed driving, it would be nice to be able to use something which is a bit more accurate. And this is where machine learning starts to come in. Okay, so the idea is we maybe want to learn a dynamics model somehow. So we're going to use machine learning to estimate a good function to approximate the dynamics. And to do this, we want to start with a decent model class. So for our example, we're just going to assume that the car is exhibiting general discrete time nonlinear dynamics. And we're also partition the state into its configuration and time derivatives, which is pretty standard in controls. And then we attempt to learn a fully connected neural network, which basically maps the current state and action to observed acceleration. So we have to learn this model somehow. And intuitively, we can think about learning this model as something like a supervised learning problem. However, learning a model that is useful for a controller like this on a high-speed vehicle is actually not super straightforward. There's a bunch of things you have to be really careful about if you're going to try to learn a dynamics model that's going to be used inside something else. So remember, our goal is to learn this function, which is going to be the f up here, parameterized by theta, that maps states and control to observed acceleration. And so the first thing we're going to do to accomplish this is just teleoperate the car around the track, right? Just collect a whole bunch of data. Now, if you're learning dynamics as just this kind of like naive supervised learning problem, you'd have an objective which looks like the one up there at the top of the slide. And so essentially you're saying, okay, I want to minimize prediction error. And the thing which is important to pay attention to here, though, is the expectation, which is related to how the data is collected. So the expectation is taken over the distribution of data induced by the human's exploration policy, whoever was teleoperating the car. And Nando actually talked about something which goes wrong when you try to do something like this a little bit earlier this morning. So the problem is that once the dynamics are learned, small errors in the learned function accumulate as MPC is executed. And this results in a trajectory that starts to stray from the demonstrated trajectories. And if MPC strays too far, then the car starts to experience trajectories that it's never encountered before. And this causes errors to accumulate even more rapidly, and then really bad things happen. Okay. So this is an instance of a problem called covariate shift, which is basically a mismatch between the training and test distributions. And this is actually extremely common in autonomous systems where robots are operating in closed loop with their environment. So fundamentally, the problem can be viewed as one where we specified actually the wrong objective here. So rather than computing the expectation with respect to the distribution induced by the exploration policy, we should have computed the expectation with respect to the distribution induced by the policy that actually uses the learned dynamics. Now, unfortunately, optimizing this can be really difficult because the parameters that we wish to update are themselves hidden inside the expectation. They affect its distribution, right? The distribution that the expectation is taken with respect to. So this becomes sort of a pretty nasty optimization problem. So how do we optimize an objective like this? And so what we're going to do is actually think about this problem kind of like a game. So we can view it as a two-player game where player one takes samples from the system and learns a dynamics model. And then the model is handed to our MPC controller, which uses it to generate actions. So it's going to try to optimize its objective with this learned model that we gave it. The control system can be thought of as literally probing the model for like exploitable errors, right? So as it does this, it generates new data, which can be used to evaluate the accuracy of the learner. The learner takes the new data, updates its dynamics model to be more accurate, and then this process just repeats. Okay, so another way to think about this problem is online learning. And this is basically Dagger, which again, Nando mentioned this morning, but Dagger for system identification. So effectively, we're fixing the distribution of data at each iteration and then solving a supervised learning problem. And the training process for our dynamics, therefore, will proceed in this kind of sequential way. So we're first going to collect data from a human driver just driving the vehicle around the track. This allows us to generate new input-output pairs. These are then added to an existing data set. So at the first step, this existing data set's empty. It's just kind of the first input-output pairs we get from our exploration. We then fit a model to this data, hand that model over to our controller. So we're going to try to attempt the task with this model, and this in turn generates new data. And then we, again, repeat this process and essentially incrementally build a data set that explores the state space encountered by our vehicle with the learned dynamics. And this results in a more robust dynamics model, which ultimately is more accurate and produces a more resilient MPC algorithm. So I want to show you some results from this. So basically, this just follows exactly what I said. So the initial dynamics model is trained from human driving. We just collect this data set of teleoperated data. That's used to train the dynamics model. That's handed to the MPC algorithm. The MPC algorithm is then set to like a fairly conservative target speed, and it uses the learned model to generate more data. That data is then added to our data set, it's added to our data set, and then basically what will happen, so here actually what you can see is the car, this is collecting the teleoperated data, right? We fit the first model, we hand the model to MPC, we run it, collect more data, train the model again, and then we do this over and over again, incrementally adjusting the objective to make it harder and harder for the robot, and it gets faster and faster at every iteration. So here you can see at test time, the result of this is a really effective dynamics model, which combined with MPC actually allows us to drive the car faster than the human could initially pilot it around the track. So it's achieving a lap time of about a second faster, which is actually 10%, which is pretty significant. And if you looked closely, you could actually see that the car is like power sliding through turns, which is pretty awesome. All right. This is also a really robust strategy, this kind of combination of learning and MPC. And a lot of the robustness actually comes from using MPC as the underlying controller. So here you can see that rock sort of knocked the back of the vehicle out of alignment, but it's able to recover. And in general, it's able to handle all sorts of rough terrain where it's bouncing and sliding. Sometimes all four wheels are off the ground as it's taking these turns really fast. All right. Okay, so in this first part of the tutorial, we started by talking about how to use machine learning to improve MPC. And we showed how you can learn a dynamics model to improve MPC performance. But in general, we can learn not just the dynamics model, but other components of the MPC algorithm as well. So for example, we could learn a cost function, maybe from expert demonstrations, or even how to optimize the model better. So think something like learning to learn. We can sort of step in and try to learn these components. The other sort of extension here is that we can treat MPC itself as like a differentiable policy class and learn things like the dynamics or the cost function or both of them in order to hit some sort of overall performance objective. So you can think about, sort of wrapping this in reinforcement learning or imitation learning, where the MPC algorithm itself is the policy. From my experience, this is actually harder to get to work in practice than just using something like Dagger to learn the dynamics model, but that's just me. Your mileage might vary. Okay, so the next thing that I want to do is kind of step back, and we're going to now look at this second way, the second perspective of thinking about machine learning and MPC. So the idea here is that model predictive control itself can be viewed as a learning algorithm, which I think is kind of cool. So the main idea is that we're going to view MPC through the lens of online learning. And note that this is different from what I just described. So it's different from using online learning to learn a dynamics model, which we just discussed. Here, we're viewing the MPC algorithm as an online learning algorithm that is optimizing the parameters of some really simple policy pi. Okay, so let's give a preview for how this works. So for online learning, each round of online learning corresponds to a time step. So at every time step, MPC can be viewed as a learner which chooses parameters theta and executes a policy with those parameters in the system. Next, we just observe what happens. In the context of online learning, we think of the system as some adversary that provides feedback to the learner by picking out a loss function that's going to be evaluated on. The learner then uses the loss to update the policy so that it will perform better at the next time step. So thinking about MPC as optimizing a policy, there's this natural inclination to think about how it relates to reinforcement learning. And it is a little bit different. So rather than learning a single policy that will work well everywhere in the environment, like in advance, instead what we're doing is rapidly updating a really simple policy at every time step that will work well wherever it's going to be applied next. Okay, so let's look at the details of how we can do this, maybe in the context of something like our car racing task. So on the left hand of the slides, we have this online learning paradigm. And on the right, we're going to specify choices for our problem. So first, each round of online learning will correspond to a time step in the system. That is, the learner will pick out a new policy at every time step. And then second, the policy is just going to be a really simple open loop control distribution. So you can just think about the policy as a distribution of trajectories or actions. Now, note that this policy is not actually conditioned on state. It's like even simpler than that. It's literally just a distribution of action sequences. And we can think of the statistics of the distribution, for example, if we're using a Gaussian, like the mean and covariance, as the policy parameters. All right. So we're also going to assume some simplified simulator, which is going to take the current state of the system and control distribution as input and produce a distribution of states as output. So using such a simulator, we can basically, as we described before, just integrate the state forward in time. And returning to our MPPI example, this is exactly what the MPPI rollouts are doing, right? We're just kind of forward simulating. But now we're thinking about this as a way of taking this really simple distribution and putting it into some space where we can evaluate it. So now let's look at the loss. So this is the expected cost under the simulated state action distribution, starting from the current state ST. So basically, what's happening is we are saying that we have some policy, which is going to be this open loop action distribution, and then the world is going to select a loss function by deciding where to play it, right? That's the state that we observe. And this might, maybe the world is perturbing this distribution around. So basically, by generating a state, the system is selecting a loss function for our policy. Okay, so then from the online learning perspective, the objective is to update the parameters to perform well in simulation at the next time step. So in other words, we want to update the parameters so that the policy will have low cost in simulation at wherever the system decides to play it, right? Wherever it decides to place me. So in order to do this, we use an algorithm called dynamic mirror descent. And this algorithm has two steps. So in the first step, it just performs mirror descent to update the control distribution so it has lower loss. That is so that we perform better in simulation at the current time step. So just a kind of really quick overview of mirror descent. It's in the family of these kind of descent algorithms like gradient descent. It's a very, very general approach. It essentially builds a convex global upper bound approximation to our objective function using a couple terms that we have up here. So it has a gradient, some step size lambda, and a Bregman divergence. And for those of you who aren't familiar, Bregman divergence is this kind of a class of divergences which includes things like the KL divergence or L2 distance and so on. It then minimizes this surrogate objective, right? This kind of upper bound that it built. So just maybe a little bit more intuitively, essentially what this is saying is we're doing something like gradient descent where the gradient basically just tells us what direction to take to update the parameters so we'll perform better. And the Bregman divergence just keeps me close to the previous solution. That's basically what's going on here. Okay. So the result is an updated control distribution which performs better in the simulator for the current state ST. We then execute the first action like we normally do for MPC. And then the second step of mirror descent or dynamic mirror descent is the dynamic part, which uses a predictive model to shift our distribution forward from time step t to time step t plus 1. So this is almost akin to something like a state space model in like a Kalman filter. And if this is accurate, then we can expect it to perform well, like our policy to perform well in the next state, right? That our distribution is going to kind of map over and do well. The online learning algorithm then just moves to the next round, which uses the newly proposed open loop control distribution together with the next state, and it just kind of continues on its way. So just in summary, this dynamic mirror descent approach views model predictive control itself from the perspective of online learning. MPC can be viewed as just applying dynamic mirror descent to rapidly adapt a simple policy at like every time step. And intuitively, if our simulator is accurate, we can predict the next state, and we can predict the next state well, then we should achieve low regret. So I won't get into the kind of the details of that, but the idea is basically this will perform better if the environment is more predictable, and it will start to perform worse in kind of a characterizable way as the environment becomes less and less predictable. Okay. Now, this online learning framework actually provides a really clean derivation of a large number of MPC algorithms to special cases, including receding horizon versions of the linear quadratic regulator, the cross-entropy method for model predictive control, and MPPI. And in each case, we can just get the algorithm out by choosing a policy, picking an objective, and then just optimizing it with dynamic mirror descent. And if you look into the details, you'll actually see that this perspective suggests that many off-the-shelf MPC algorithms are actually suboptimal, which is super interesting. So from an optimization viewpoint, they make a number of heuristic choices which are not necessarily well justified. An example of this is step size, which is hidden in the usual stochastic MPC derivations, but an important component to getting optimization to work well. The perspective also provides a very prescriptive approach to model predictive control design. We can easily generate new algorithms that make sense for a particular application by just using different choices for our underlying policy or our per round loss, the divergence, and so on. Okay. So using insights from this dynamic mirror descent approach to MPC, we're able to better tune optimization and generate new algorithms. So for example, we can generate a new variation on MPPI that can reduce the number of samples needed to control our car on a dirt track racing task by almost 2 orders of magnitude. So this is just using 64 samples it's rolling out instead of almost 2,000. And this allows us to use much less compute and scale MPC to higher dimensional problems. I also want to show you like a little bit more recent work. So we've used insights from dynamic mirror descent MPC to design better MPC algorithms for higher dimensional control problems, like the control of a manipulator. So an example of this is our paper Storm, which is actually here in this conference, which uses MPC as a core component of a system for really fast reactive control of a manipulator. And we add a number of improvements, including quasi-random sampling and covariance adaptation to make the optimization more efficient. And the paper will be presented here at the conference on Thursday, so you can learn more about it then. Okay, so let's step back again and take a third very different learning-based perspective on MPC. As we've seen, MPC requires a number of choices for it to work well. For example, like the length of the horizon, the accuracy of the simulator, or even the number of samples used in sampling-based MPC methods. So if, for example, the planning horizon is too short, MPC is myopic, like literally, and it fails. It cannot see far enough into the future in order to make a good decision. So here are 2 just really simple examples of this on synthetic like robotics problems to illustrate the type of failure that this can cause. So on the left is a pushing task where the goal is to push the dark block to the red goal position. And in this case, due to the short horizon, the manipulator cannot even reason far enough to move itself around the block in order to like push it to the goal. So it just kind of is spastically just sort of moving around in the goal region. On the right is a ball and cup game where the object is to swing the ball up and catch it in the cup. And if the reward is sparse, you get reward when the ball is caught. the longer a longer horizon is actually needed in order to discover regions of high reward. And in the case which we kind of see here, the horizon's too short and the agent just kind of swings the ball around randomly. All right, so how can we solve this problem? So there's one really easy solution, right, which is just to lengthen the horizon. This might be too computationally expensive, though, for real-time optimization. If our horizon is long, we might not be able to actually compute it fast enough to be able to control a fairly dynamic robot. And we also need to possibly solve a harder optimization problem, or methods like MPPI might need prohibitively many samples to converge to a good solution. So there's a number of problems with making the horizon too long. We often want to kind of keep it as short as possible, just for speed and agility. Okay, so we can actually attack this problem with a different approach. And to do so, I want to look at this connection between MPC and reinforcement learning. So we've already seen that MPC can be viewed as optimizing a policy. For example, at the current state, we saw that a robot can use an approximate dynamics model and a cost function to optimize the parameters of a really simple policy, like a Gaussian distribution. But MPC can also be viewed as locally approximating the expected cost to go at a given state for many actions. So in other words, the Q function. So from a reinforcement learning perspective, we can then just view policy optimization as being accomplished by constructing a surrogate MDP, which we're going to call M hat here, with different dynamics than the true dynamics, right? It's whatever our simulator has, and some cost function. So this is going to be our cost in simulation. That's the C hat, and some finite horizon H. MPC then forms a local estimate of the Q value as the expectation of our discounted cost over our horizon H, followed by some terminal Q estimate or terminal cost in the surrogate MDP. So the definition of the Q function is given here sort of at the top of the slide. Basically, it just says that we can write the Q function as the expected sum of discounted costs over our horizon H, and we have this terminal cost or terminal Q function. Okay. The optimization step in MPC attempts to find the optimal policy parameters, which we're going to just call phi star here, to minimize this cost to go. And then we execute a single action from our policy. We get feedback from the world, and then the process is repeated at the next system state, resulting in this feedback controller. Okay. So the key to overcoming the challenge of a finite horizon without actually extending the horizon is to just pack all the expected cost to go into the terminal cost or Q function. So this is the basis for so-called infinite horizon MPC. And what we can do is, while we're running MPC, we can collect data and use reinforcement learning to estimate the Q function for this terminal cost. Like, this can be just happening in the background. And as we do that, we're going to have a better and better Q function, which then gives us, if we just hand it over to MPC algorithm, a better and better performing MPC algorithm, because it's starting to learn beyond the length of its rollouts. Okay, so we can solve the problem of having too short a horizon, but there are other ways in which MPC can fail. So we already saw that having an incorrect or biased simulator or dynamics model can be problematic. So in the early part of this tutorial, we proposed a way of learning the dynamics model from data. However, even this model can be biased, right, if we choose too simple a model class. So we can simultaneously overcome model bias while increasing the effective horizon of MPC by blending in a learned value function at every time step along the horizon. And a blended Q estimator can basically construct an H horizon estimate as an exponentially weighted average of all horizon estimates from 0 to H. And it does this using a parameter lambda. So those of you who are familiar with reinforcement learning, this looks something like the TD lambda method. This causes shorter range predictions to rely relatively more on the model from MPC and longer range predictions to rely relatively more on the estimated Q function. My TV will be turned off in 1 minute. Okay, I'm almost done, so that's all right. We can further see that by basically changing this lambda, we can tune the horizon length different ways. So, for example, when lambda equals 0, the algorithm reduces to only using the learned Q function. There's no like model rollouts. And when lambda equals 1, we're going to recover just our standard MPC algorithm with the Q function at the end. And anything in between allows us to smoothly interpolate between these two extremes. And this leads to another powerful insight, which is that we can implement MPC to control a robot, and this is already good, so we can start with this. But as the robot operates in the environment, we can learn a Q function and slowly start to decay lambda as the Q function gets better and better. So we can start with something which works really well, and then we can use data to just improve. And this will potentially remove model bias as we encounter more data, while also reducing variance when used with sampling-based MPC. And again, this is similar to TD lambda. Okay. My screen's gone, but that's fine. We've completed a number of experiments in simulation, which basically just shows that this is a really powerful strategy which works in simulation. We're currently working on implementing this approach to enable real systems, like some of the ones you saw earlier, continuously learn and improve MPC. So we're sort of viewing this as just kind of initial exploration. All right, so just in summary, we explored MPC as a powerful paradigm for controlling robots in uncertain dynamic environments. We looked at how MPC could be combined with machine learning in several different ways, using machine learning to learn a model within MPC, showing that MPC itself is a learning algorithm, and wrapping MPC inside of reinforcement learning so that it continuously improves with data. And just kind of in summary, I think we've only really started to scratch the surface here. There's a lot of different ways that machine learning and MPC can interact. And I think this is going to be a very powerful way to integrate learning, real-time simulation, and control on autonomous systems. All right, so finally, just to conclude, I want to thank the PhD students who I've worked with on projects in the intersection of machine learning and model predictive control. And all of their work really led to the insights that I have on these problems and what I discussed today. Thanks. I'm happy to take questions.
We'll start with the questions from the room. So are there any questions here before we go to the online questions?
Thanks for the very nice talk, Byron. So you showed that MPC is a really cool online learning algorithm. There have been a number of works in the field suggesting that this can be distilled into a neural network or something to improve the policy further. So my question is, do you think that in general you should always be using online MPC type planning, even if you're doing this distillation process, or is there a point at which the distillation can just take over the MPC?
So that's a great question. I think it depends. So we've used distillation before as well, and it can make sense, especially if you're trying to control a vehicle with different types of state, right? So maybe I don't want to use GPS, but I want to use vision or something like this, and I can distill my MPC policy into a neural net. I think the major challenge is due to generalization. So one thing which is nice about an MPC algorithm, if you have like a decent dynamics model, we can assume that that dynamics model is actually going to work well in a wide variety of scenarios, even ones which we haven't encountered before. So in order to do distillation well, you either have to sort of learn the entire MPC algorithm by sort of running it through many possible scenarios in simulation, or you would be distilling it for a certain area of your environment or state action space. I think it could work, but you just have to be just kind of careful about how you do that and what you're assuming about the distribution that you're going to encounter at test time.
Yeah. Byron, thank you. That was great, crystal clear. And I'm curious about the model of uncertainty. So the system, you didn't really talk much about modeling uncertainty as you go, but I'm curious because it would be state dependent, I would presume. So when you're, for example, the lambda, tuning lambda, you don't just want that to start at 1 and go to 0. It seems that you want it depends on where you are on the track. So there's certain areas of the track which you really need to fine tune and you have more uncertainty. You want to go back there and do more exploration. Others that you kind of got it down. So I'm curious if you could say a little more about how you would systematically tune and use lambda as you're during the exploration process.
Thanks, Ken. So I think that's a great insight, and that's definitely true, right? Like in some areas of the environment, like I either know MPC works really well, or I've just nailed the Q function because like right around the center of the track, let's say. But then I want to actually use my model in new areas where I haven't like seen that much data. I think that's absolutely right, and having a state-dependent lambda is really the right way to go. And we've thought about this a little bit, but I think it's basically just wide open for the taking. Like, you should do this. I just think it makes a huge amount of sense, and actually it's a really interesting way of combining maybe real-world data and simulation. And you can be using simulation to kind of like keep you out of dangerous areas. So you can be using it to sort of do those rollouts while using real-world data to ensure that you're operating as efficiently and optimally as possible in areas where you have seen a lot of data. So I think it's like a really good thing to try to do. It's been in my mind. I maybe need more students to attack that.
Right, thank you for the questions. Let's take some questions online.
Yep.
All right, I think we have one already. Roberto, are you there?
Yes. So we have online here a question. In what cases would you want to use an evolutionary strategy, CMAES, rather than a convex optimization method?
So I want to be like fairly agnostic about what sort of optimization you should use. You should use whatever is correct for your problem. We found that if you want sort of like really high frequency MPC, like 500 hertz or something like that, and the objective and dynamics are kind of like simple enough, you should just use like a really fast convex optimizer. For some of these problems where we don't have to be quite as fast and we have pretty complicated costs, it might be easier to optimize it with CMAES or similar types of non-convex optimization strategies. But I think that's one of those things where depending on your task, you want to think hard about the problem and then choose the right optimizer. It's not going to be like a one-size-fits-all thing. So a good example of this is like the MPC algorithm that Yusheng's using for like the low-level torque control of the quadruped is convex. Basically, MPC is convex optimization. And then for some of the stuff like off-road driving and dirt track driving, we're using, we have these more complicated objectives and dynamics, and we're using something which is more like CMAES.
Okay. Thank you for your answer. Then, in this case, thanks again, Byron, for the excellent tutorial. And we will be moving to the next speaker.